Several years ago, I was in a car waiting for the traffic light to let us proceed forward. I was passing the time by watching the traffic crossing in front of me, and for one split moment I noticed a car to my left, some distance from me. I looked away for a few seconds, and when I looked back, I saw the same car again, though it was much closer to me. At that point, I began to think about what conclusions I could draw about the car's position outside of those two moments. For instance, using what I observed, could I predict where the car would be 1 second after my final observation? We only have two data points, so we really don't have enough information about what the car's motion looks like to answer such a question. For example, it could be accelerating, decelerating, or have a constant speed. It's possible that different motion behaviors of the car could allow the car to reach each of the points at the same time, though have different final positions at a set time afterwards. Let's slow that down some to really observe that. Perhaps then it would be more interesting to focus on estimating the car's position between those two moments in time, as that behavior heavily influences future motion. Making estimations of data between known data points is known as interpolation. This is in contrast to trying to predict data outside of our observed data range, which is known as extrapolation. Let's analyze this situation and see how we might interpolate the car's position between the two moments we observed. Let's first get a graph set up to help us analyze the car's position with respect to time. The x-axis represents the time that has passed in seconds, which we'll denote with t. The y-axis represents the car's position on the road, and we'll denote this with f of t, as the car's position depends on the time that has passed and is therefore a function of time. For now, we'll say that the car's initial position at t equals 0 is 0, and that the car traveled for a total of 3 seconds to end up 45 meters to the right of that initial position, which at t equals 3 is 45. Yes, I do love the metric system. To simplify our model some, we'll assume that the car had a constant speed during its travel time, which, if we trace that out here on the graph, we see is a straight line. With this model, we can estimate that at t equals 1, the car was 15 meters to the right of the initial position, and at t equals 2, the car was 30 meters to the right of the initial position. Using a straight line to do our interpolation like this is aptly called linear interpolation. Let's try to generalize this situation some. We'll say that the car starts at a position A and ends at a position B after tf seconds, the f in the subscript meaning final. Keep in mind that A and B are just values between which we're linearly interpolating, so if B's value is technically less than A, like this, we could just imagine flipping the graph vertically so that our start value is always on the bottom. Okay, back to our original graph. To further help visualize that A is the start position, we'll shift our view of the graph up so that A is at the bottom of our visible y-axis, remembering that this doesn't mean that A is equal to 0. We'll also scale our view some so that B is at the top of our visible y-axis. Since we're trying to generalize everything here, we should realize that the total time on the x-axis varies between different situations, so let's make the x-axis time independent by normalizing time to start at 0 and end at 1. This makes our graph's input of t now represent a percentage of the car's journey from the start position to the end position. Thus, we've generalized our graph to represent that at t equals 0, the car is at position A, and at t equals 1, it's at position B. Now, how about we start modeling all this mathematically? Since we have a straight line, we can use a linear equation of the form y equals mx plus b, where m is the slope, b is the y-intercept, x is the input, and y is the output. Since we're already using the variable b to represent our end position, we'll change b to c for the y-intercept. Also, since the input is t and the output is f of t, we'll change the equation accordingly. Our slope m is the change in the y values of the 2 points over the change in their x values, which is b minus a over 1 minus 0, which simplifies to b minus a. The y-intercept c is the y value attained when t equals 0, which is just a. We can now put the calculated slope and y-intercept into our equation, and with some expansion, rearranging, and factoring, we've transformed the equation into the quantity of 1 minus t times a plus t times b. Even though the start position of A and the end position of B are constants for our situation, we can generalize this even further by making A and B additional variables in our function. So, we have successfully modeled a function that linearly interpolates a specific percentage t, also known as the interpolation factor, between a start value A and an end value B. This function is commonly used in many computer applications, and is usually available to programmers in this form by the name of lerp, which comes from the letters in the words linear interpolation. A fun way to visualize linear interpolation's effect is to choose a start and an end position for our car to travel between, and then imagine that we have a slider bar that controls the interpolation factor. We could use this slider bar's value to linearly interpolate the car's position between the two positions. In fact, if we move the slider bar uniformly from 0 to 1, then we see that we're animating the car's movement with a constant speed between the two positions. We can also modify how fast we move the slider bar to have the car arrive after a specific time interval. For example, if we want to animate the car traveling between t equals 0 and t equals 1 for 4 seconds, we calculate that we would need to move the slider bar 0.25 per second. Thanks to linear interpolation, we have an easy way of animating position, requiring only a start position value, an end position value, and how fast we want the animation to occur. We can also easily extend this animation to 2 dimensions by linearly interpolating between 2 x values and between 2 y values separately, but using the same interpolation factor between them. So far, we've only really thought about animating position using linear interpolation, as its effects are easier to observe. But there are so many other types of values we can animate. For example, we could animate the visual scale of some text to make it pop in and out. We could also animate the changing of an object's color by animating changes in the color's individual red, green, and blue channels. This is all great, but there is a bit of an issue with our animations. I don't know about you, but I've never seen a car just instantly have a non-zero speed and then later just instantly stop. It's just not realistic. By choosing to linearly interpolate with a constant rate of change, we have made it easy to model animation, but have produced rather bland-looking, unrealistic results. However, instead of a constant rate of change from t equals 0 to t equals 1, notice what happens if we apply a constant acceleration to the slider bar to slowly increase the rate of change. The car's movement is much smoother. This doesn't do anything for the sudden stop at the end, but let's move the end position to just off the screen, focus only on the car, and watch again. Isn't the car's motion much more natural looking now? Let's analyze this by sampling the interpolation factor values at even time intervals and plot them on a graph. We see that the resulting curve is a smooth quadratic curve, the kind that mirrors the position graph of an object under a constant acceleration, which is what we were going for. What we've built here is a function that maps the constant rate of change for the interpolation value to a smooth, nonlinear rate of change, enabling us to transform simple linear motion into more natural and interesting motion. In fact, we could try all sorts of different curves here to animate nonlinear motion, like deceleration, a smooth speed up and slow down, or even a crazy elastic effect. To ensure that we always get from the starting value to the ending value, we need to constrain the function's value at t equals 0 to be 0, and the value at t equals 1 to be 1, but we can vary the behavior in between almost however we want. These types of functions are known as easing functions. When we use an easing function to first modify the interpolation factor before using it as an input to the linear interpolation function, mathematically we are partially composing the linear interpolation function with that easing function. The need for easing functions is so common that there's actually a set of them that have a common naming structure. Going back to the easing function we built before for a smooth acceleration from rest, this function is known as ease-in quad. The ease-in part means that there's an easing in at the start of the function, or in other words, a lower rate of change at the start of the function with a higher rate of change at the end. The quad part means that the function is constructed using a quadratic function, instead of something like a cubic, sine, or exponential function. The ease-out quad function is similar in that it's also built from a quadratic function, but there is an easing out towards the end of the function, with a higher rate of change at the start and a lower rate of change at the end. A combination of these two types that uses quadratic functions would be the ease-in-out quad function, which means that there is both an easing in at the start of the function and an easing out at the end. In other words, there is a lower rate of change at the start and end of the function, but a higher rate of change in between. Each base function from which easing functions are created, like the quadratic function here, have these three variations. Some other examples of these functions would be the circ ones, which are based on the shape of a unit circle, the back ones, which overshoot their target and then ease back, and even exotic ones like bounce, which model an object bouncing to a rest. By using and combining these easing functions, we can make animations like these feel awesome. If you do any software engineering and are curious about using linear interpolation in your code, keep in mind that software libraries use various names for the lerp function, like interpolate, mix, or blend. In the worst case scenario, remember that we derived the lerp function ourselves, so it ought to be rather straightforward to implement it in code from this. Also, if you'd like to explore more about easing functions, easings.net is a great resource for the most commonly used ones. The site has animations to visualize each function, and even has the math behind each one if you need to implement them yourself, or even if you're just curious. With all that said, thanks for watching.